This is going to be a tutorial on how to use Stata to do simple linear regression. And for this one, I'm going to use the data set that I provided on Blackboard under Computer Examples folder in Simple Linear Regression. Computer example number 2. We're going to do number 1 in class, so I'll just pick a different one for this little session. This one is actually a little fun little data set because this one's not really in social sciences. This one is just, it's one I borrowed from biology, but still an interesting little study. Somewhere along the way, someone discovered or noticed that it seems like the rate at which crickets chirp changes with the outdoor air temperature. And now this is kind of a very a dumbed down version of the original study, so this one's kind of simplistic, but it's enough to get the point across. So what we've got here is we have two variables. One is temp for the outdoor air temperature in degrees Fahrenheit, and the other one's chirps. That's the average number of chirps per minute that a cricket makes. You can read the details of this if you like, but basically a researcher collected a sample of 20 crickets, and on different occasions he took one of the crickets outside and counted the number of chirps over a 10-minute span, and so took that and divided it by 10 to get the average number of chirps per minute, and so that was to serve as the dependent variable. And then he recorded the air temperature on each of those nights, with the idea that they would probably chirp faster on warmer nights. Was I believe there was actually a lot more to it, but to make it simple for us non-biologists, let's just say they were chirping faster if it was warmer out. So let's open up your Stata, close that. Okay, now I've already got the data file open in here, but if you go to Blackboard, it'll be the Simple Linear Regression, or SLR, computer example number 2. So, okay. So the first thing we're going to do, first thing I like to do whenever I have, excuse me, when I have a regression situation is, I will typically go to graphics, and then I want to do a scatter plot, and the easiest way to do that is actually the first one here, which says two-way graph, and has scatter line, etc. in the description. Well, they call it a two-way graph. That's just Stata's name for it. Two-way meaning that there's two variables involved. In this case, an x and a y. So what we'll do is when we click that, look, this little box opens up. We'll click Create, and it'll automatically it should be selected where it says Basic Plots here and Scatter here. And so the variable we want on the y-axis is usually our dependent, so I'm going to put chirps there. And for the x variable, I'm going to put temperature there. And that's all we need to do. Now hit click Accept, and it'll bring us back to this box. Now it does this because you can actually overlay many plots. So you could actually create another plot to go over this, but that's a little bit more of an advanced topic right now. So let's just leave it at this. We just want to see the scatter plot by itself. And we'll click OK. Okay. And there we have it. It looks, well, kind of looks like a fairly linear trend actually, so fairly closely packed around what it would be a center line. So I'm going to close this because I'd like to actually put the regression line in there. So I'm going to open this back up. And when we do this, you're going to notice that it has that plot 1 in there already. If I want to do a scatter plot with a regression line in it, I'm going to leave that. Plot 1 is my scatter plot. I'm going to hit Create again. And over here on the left, I'm going to select Fit Plots. And then in the list over here, I'm going to select Linear Prediction. And so I'm just going to put these, as we did the last one, chirps in the y and temperature in the x. Accept that. And I see it has two plots on here. And it's just going to combine these was going to lay one over the other. It's going to lay the line over the scatter plot. Like that. And so that's our regression line. Even though we haven't actually done the regression analysis yet, it does the basics and puts the line in there for us just so we can see it visually. And so we can sort of get an idea here already that it's a fairly linear trend. My guess is the homogeneity of variance is not going to be an issue, so we can probably assume that. No odd clusters, so nothing strange going on here, no odd patterns. So it's not that much data, but still nothing out of the ordinary. So no influential cases most likely, and no reason to suspect that we have a problem with independence. So, okay, well, I'll close that. Let's go on to the actual regression itself. So to do that, we're going to go to Statistics, Linear Models and Related, and Linear Regression. And another box pops up, and it says dependent variable, so the chirps. Independent variable will be the temperature. And let's see, anything else we need to change on here? Don't think so. Nope. So that's pretty much all we need to do, so we can just click OK. And here we go. Here's our basic output for our simple regression analysis. So what we have here is kind of a compact table of things. So let's address some of those the major components that we're always looking at for whenever we do a linear regression. Well, one thing we're always going to be looking for is the R-squared, or squared correlation coefficient. And at this point, we only know of one kind, and we just call R-squared. You could call it the unadjusted R-squared if you want. It doesn't say that up here, but here it is. It just says R-squared and 0.7464. So roughly 75% of the variance observed in the chirps, in the amount of chirps made by the crickets, can be explained or linked to the temperature. Okay, well, and then the F-test that goes along with that to tell us if that R-squared is really significant or not is right here. And this one's kind of nice because it actually goes ahead and tells you that it's an F-test with 1 and 18 degrees of freedom. So that's just like with the ANOVA, there was always those two parts to the degrees of freedom. So here we would call this one the degrees of freedom of regression, and we call, which is 1, and we'd call the degrees of freedom for the residual or error would be 18. And then the value of the F-test itself is 52.98. And then the p-value associated with it is right underneath it, which is 0.00. So it's very small, obviously, so it is significant. So we can go ahead and say that our model significantly predicts the chirping rate for crickets using temperature. Now, that was the R-squared. If we want to look and talk about the relationship precisely of temperature and chirps, well, we would have to go look at the regression weight, or the regression coefficient. And so that's the regression coefficient is associated with the independent variable for the purposes of predicting or explaining the dependent. So that's why on this line it has temperature, which is our only independent variable. It has a coefficient here, 3.4596. This is the regression weight, 3.46 rounding. And then on that same line, there's a t-test and a p-value again. And it's a tiny p-value, so that means that estimate for the regression weight there is statistically significant. In other words, it's not 0, or it implies that it came from a population where the regression weight isn't 0. So in other words, there is a relationship between temperature and the number of chirps the crickets make, which was really what was implied by the earlier test when we were looking at R-squared. And that's going to be the case when we have just the one predictor. The p-value that we get for the for the r-squared is going to be the very same p-value we get for the regression weight, because they ultimately represent the same thing. That's going to be a little different once we get to multiple regression, because there are more than one predictor variable. And finally, there is another line here it says CO and S. That's short for constant, and that's just what Stata calls the intercept. And a lot of books and authors call the intercept the constant, so that's not an unusual term. So, but the intercept is that value right there, negative 176.7425. And there is a t-test and p-value associated with it, which most of the time, especially in social sciences, we don't really have a lot. I mean, it is occasionally useful at times, but for the vast majority of times, from what I've seen, it usually is not. People aren't too concerned with it. It usually is not a research question they're wanting to address. Occasionally it is, and it will be in advanced techniques like SEM, but for now, it's just not an issue. And I mean, it's testing the idea is the constant 0 or not 0. So, okay. So that's the basics of the regression analysis itself. So let's do some things where we need to check some assumptions. Now, usually we would probably want to check assumptions before we ran this anyway, but so many of these in Stata require this to be run first, so they can use the model that's been computed and get stuff out of it and check certain things. And in fact, one of the things we'll need to do first is compute some residual scores, so the residual values for each person in the data set, and we'll also compute the Cook's distance values as well. But in order to do that, we always have to have run this main regression command first, because that's how we get our predicted values, how we get our residuals, and how we get, well, pretty much we need this to get the rest of our solution. This is the main solution, but to get other pieces, we usually have to have this done first. One thing we can do right away is, and there's a couple ways to get to it in graphics, we'll go to regression diagnostic plots and residual versus fitted. This is the residual plot. And really just click that. It opens up this box, and there's really nothing to select here. You just leave it alone and just click OK. Now, what we have to pay attention to is the line, the horizontal line where it hits 0 here. So this is kind of the scatter plot if we've just turned the line completely flat, and the line that comes out as 0 right here horizontally, that would represent our regression line. And so we kind of want to look at the way that the points scatter around it. Is there anything unusual? Is there a curve pattern, or a boat, or anything strange going on here? And it looks fairly consistent. It looks like the variances on the far right end may be a little greater than the variances down here, so that may be a bit of a horn pattern. I'm not sure about that one, so possibly an issue. Again, no odd clustering or anything to indicate any problems with independence. And linearity, of course, yeah, I've already covered that, so that seems to be fine. So I'd say this looks pretty good. I might be concerned about homogeneity of variance. If it were a larger sample, it'd be different. But I may actually, well, just for the sake of demonstration, I'm going to run the statistical test for homogeneity of variance anyway, just to check. But this could, if you kind of squint and look at it, you can sort of see it sort of has that cone pattern that gets larger as you go to the right. But otherwise, it looks like it. And even then, it's not that bad. So let's check that while we're thinking about it. So how do we check that in Stata using the menus? Well, we'll go to Statistics, and all the way down here to Post Estimation. And there's a Specification, Diagnostic, and Goodness of Fit. Open that one up. And there should be tests for it calls test for heteroskedasticity. The homoskedasticity was just another word for homogeneity variance. and you could also say you're testing for heteroskedasticity, or violations of homogeneity variance. So that's the one we're going to select. I click launch, and then the one should be selected automatically. So it should say Bruce Pagan / Cook Weisenberg. It depends on who you want to give credit to, but I've always known it as the Bruce Pagan or the BP test. And so anyway, that's all we need, and I'm just going to click OK. I'll close that back, and look, well, it looked like there might have been a problem, but I guess not. So because that test is not significant. And again, you don't have to do both. Analyzing or assessing the assumptions visually using the graphs is fine. I typically myself use the test because it's, well, a little faster and not so subjective. And I often would look at the graphs anyway, and like I just was saying, it looked like there might be a little bit of a problem with homogeneity variance. But again, I was wrong. Visually, it was not really there. Not enough to cause this to be significant. So there, good, we're okay with our homogeneity variance assumption. Okay, so for the other test that we're going to have to run, or the plots we're going to generate, we're going to need to generate a couple variables. One is going to be the variable for the residuals. So basically we're going to create a new variable that's going to contain the residual values. So how do we do that? Well, we will go to statistics, post estimation again, and then we'll go down here to the option that says predictions, and there's a option in there that says predictions and their standard errors, leverage statistics, and so on. Let's click launch. Okay, this other box is going to open. It's going to ask for a new variable name. You can call it whatever you want. I usually name it E, but you can call it anything. You can call it res for residual or anything. I'm just going to name it E. Now, after you do that, there's a list of different things on here. Here, this second option now where it says residuals, equation level scores, just click that. There's standardized and studentized residuals, which have their uses, but for now we'll just stick with just the regular residuals. So as long as you named it and click that option, you're good. So click OK there. Now it doesn't really do anything. I mean, it echoed the command back to us, but didn't do anything. Well, that's exactly what's supposed to happen. What we can do is, you notice over here on the left, a new variable's been added, E, and it gives it the label residuals. I'm going to open up the data file now and take a look, and it has computed all the residuals for each person, or each cricket. So there are 20 crickets, and this was the distance each observation had from the prediction line. Okay, that's what we were wanting. So let's use that one. So okay, so what can we do with this? Well, we can look at a histogram to see if normality is an issue, or a box plot if you like. So let's do that. Let's go to graphics and go to histogram, and then under variable, just select E, because we want to look at the distribution of the residuals. In other words, how are these things distributed around that regression line? And so we can do that and from there you can just click OK. If you want, you can, if you go to this tab over here, it says density plots. If you click on that, there's an option that says add normal density plot. It will draw an idealized normal curve over that, if you like. So I'll leave it on just to show you what it does. Let's click OK. And see what it sort of tries to center and draw a normal curve for reference. And again, this is a small sample size, so it's kind of hard to interpret these histograms because you have a bunch of blocks here in the middle and it's hard to tell. It looks like it probably may not be normal. So this one's kind of, it's hard to read on this one. So I'm going to close that, and Yeah. At this point, I would be hesitant to say that normality is met because that doesn't look very symmetric. But the thing is, there's so few data points; it's really hard to say. So I'm going to run a test for normality, which we can get if we go to statistics, summaries, tables, and tests, distributional plots and tests, and go down here to the Shapiro-Wilk normality test. And the variable we want to test is E, the residual. And that's really all we need, so we'll just click OK. Well, so I was wrong again. So visually, that graph didn't look very normal, but it's not. It just doesn't have enough data to be able to definitively say that it's not normal. So it doesn't appear to violate the normality assumption to any great extent because the p-value here is greater than 0.05, so clearly not significant. So we can't really claim that there's any problem with normality. So we can go and assume that we have met normality. So the Shapiro-Wilk test is it's kind of like the other assumption tests that we've done in the past, like Levine's test and the Brown-Forsyth. The null hypothesis associated with this thing would say something simply like that the population that these data are sampled from is normally distributed. So in other words, there's no difference from what we have and what this idealized distribution is. And so if we get a non-significant p-value, then we have to retain the null, which says it appears to be normal. Doesn't prove it, but it gives us evidence. At least it doesn't look like it's has made such a departure from normal that would mess things up. So okay, so we look good there. Let's see what else can we do. We actually do need to look for influential cases or extreme values that could throw off. Now visually, when we looked at the scatter plot, it didn't look like there was anything unusual, and it probably isn't. But it's still a good idea to go ahead and compute Cook's D, or Cook's distance, for all the individuals in the data set. So how we do that is we go to statistics, post estimation, and back down to predictions. And predictions in their standard errors leverage statistics, same as we did before to make the residuals. So the same the stuff is still in there. So instead of E, I'm going to put the letter D in there for Cook's distance. And again, you can name it whatever you want. You can call it Cook or whatever. And then I'm going to select the option down here that says Cook's distance. Oh, that's all we need. Okay, and I don't need this box anymore. You notice it didn't do anything other than echo the command back to us. And you notice that we have a new variable in here. Once again, D, and it's labeled Cook's D. Let's open it up. So if you notice, now we have all these Cook's D values, these Cook's distances. With a small data set, this is easy to look at. If you remember, if any particular case is extreme or has too much influence or leverage on the regression equation, if it's tipping it over or something, its D value, its Cook's distance, will be greater than 1. Now, a small data set, it's easy to come in here and just kind of scan through here and say, nope, nothing really big, no one's greater than 1. So, okay. So that looks fine. Well, let me close that out. And that's easy to, okay, so we can say that now. It doesn't look, none of our cases have any particular excessive influence, or, there's no outliers that mess up our regression solution. If you wanted to, you could do, if you had a big data set and you didn't want to, with thousands of people, and you didn't want to go through there one by one and try to figure out which ones, if there was someone in there that had a D value greater than 1, you could go to statistics, summaries, tables, and go to summaries and descriptive statistics, and then just finally to summary statistics, and put D in that box and click OK. And you do that, you'll get some very basic descriptive statistics for that variable. The one that is most useful, though, where on the very end where it says max, the maximum value, the maximum Cook's D is 0.167, which means that if that's the largest that's observed in this data set, then obviously no one's greater than 1, so we don't really have to go looking. If the max value was greater than 1, that means that one or more people, or in this case crickets, would have had a large D value, and we'd have to go track them down and figure out which one's which. That's a handy little trick whenever you have large data sets. Now, that appears to be all there is for this. I will make there will be a separate video that discusses prediction and confidence intervals and prediction intervals. I'm going to keep it separate from this one because this is just the basic regression analysis. You don't always do prediction whenever you do regression. So anyway, so this is the basic one. I'm going to conclude this one here, and there will be a follow-up video that handles prediction.